So the last presentation before the break, the topic is high frequency PCB winding transformer design with medium voltage insulation for solid state transformer. And the presenter is Zheqing Li, and he received his BS degree from Zhejiang University in 2018, and he's now a direct PhD student at CPES, and his research interests include solid state transformer, high voltage insulation, and resonant commutator. So, please, Zheqing.
Hi, everyone. This is Zheqing, and it's my honor today to give you a presentation on the high-frequency PCB-Winding transformer design with a medium voltage insulation for the solid-state transformer. And today I will talk about this in 4 parts. The first, I will just give the introduction and some challenges of these Litz wire transformers in the solid-state transformer application. And then I will talk about this proposed PCB-winding-based transformer design for solid-state transformer. And then I will talk about some fabrication process for this transformer winding and some experimental results. And then summary and future works conclude my presentation. The solid-state transformer is an interesting topic at this moment to directly step down the medium voltage from the grid to the data center or fast charging applications. The most typical applications of the prototypes have a 2-stage structure. The first stage is the cascaded H-bridge circuit, and the second part is an isolated DC-DC stage. With the help of this solid-state transformer, we can directly step down the medium voltage AC to the low voltage AC to achieve a smaller footprint and a higher efficiency. Compared to, if we just take this data center as an example, if we consider the traditional low voltage AC power distribution, and we will say there are many power conversion stages. And due to these many power conversion stages and have just each relatively lower power efficiency, and we will say the entire system can only achieve the efficiency at around 80%, which is a relatively inefficient system architecture. However, if we consider the future power distribution system in the data center, and we can just have this scalable system with a DC bus, such as this 400 volts DC. With the help of the solid-state transformer, we will step down this medium voltage AC through the solid-state transformer and come to this 400 volts bus. And also the PSU and VRs are all placed on board. In this case, we can minimize our power conversion stages. And also, due to these minimized power conversion stages, we can just have an increased efficiency, which can achieve 90%. And compared with the previous AC power distribution case, we can have achieved a 10% improvement on the total efficiency. This page shows some previous achievements on our DC-DC state design of our previous exercise. Take this 4.16 kilovolts input as an example. The design is based on 800 to 400 volts, and the power level is 15 kilowatts on the resonant converter. So if we just design this one for a 15 kilowatts per each module, and we can achieve around 225 kilowatts for the 3-phase system, and it's a scalable system, and we can easily enlarge the power level by parallel multiple twice, by multiple. Oh, sorry, I don't know what happened for the light. And as for the peak efficiency, we can achieve 98.8, and the power density can reach 3.7 kilowatts per liter. And as for the design for this kind of 4.16 kilovolts input, the insulation is another concern with the solid-state transformer applications, and the partial discharge free level can be achieved up to 9 kilovolts. However, here is some issues for this complicated insulation manufacturing process. As we can see here, if we would like to build a transformer with a high voltage insulation, especially for the solid-state transformer with a high frequency operation, we will first wind this winding on the bobbin, and then we should place this one in the mold and to pour the epoxy inside the mold. And finally, we should apply the shielding and stress grading layer to control the E field inside the primary side winding coil. The entire system insulation fabrication should be just cured in this vacuum chamber to eliminate the air voids. And this part just is very complicated and it's hard to control the air voids, which directly leads to a lower partial discharge level. So in order to avoid such a complicated manufacturing process, our solution is that we can use the PCB-Winding-based transformer instead of the traditional Litz wire case. For the insulation structure, everything is quite similar. And we use FR4 as the insulation layer, as we can see in this yellow part. And we still apply the shielding layer and the stress grading layer as our previous exercise in the Litz wire-based transformer. From the section view, we will see this yellow part is the FR4. And the dielectric strength for FR4 is around 45 kilowatts per millimeter, which is almost 2 times higher than the epoxy. So the insulation layer thickness can also reduce 50% with FR4. And also the fabrication is much more straightforward because we can just easily apply this additional FR4 layer during the manufacturing process in the PCB. Here comes the first highlight with this PCB-Winding-based transformer is its easy fabrication and the lower thermal resistance. Compared with the Litz wire-based transformer and the PCB-Winding-based transformer in the section view, we will say there is no complicated bobbing inside the insulation architecture, and all the insulation can be achieved with this FR4. And also, compared with this kind of Litz wire-based PCB, the thinner insulation and the larger cooling area leads to a smaller thermal resistance, which is also critical for the thermal management. Another beauty for this one is a lower profile design, as we can see in this part. The PCB-Winding-based transformer can easily to reduce the height of this transformer to further increase the power density. However, there should be one drawback for the PCB-Winding, and we cannot avoid, is the PCB-Winding will significantly lead to a greater winding loss, and how to control this one should be a key issue for the PCB-Winding-based transformer. So to solve this one, we may just start from our just core structure. Previously, we just always prefer to use this kind of UI core structure, and all the flux will only have one flux path. And if we consider this flux distribution, and we will say there is a 2 hot pots, and this part will just lead to kind of high eddy current loss, as we explained in our previous annual conference. If to improve this, we can just switch our UI core into the ER core. Actually, in here, there should be another just upper plate, but just I would like to just show this kind of winding structure, so I just eliminate this part. As we can see here, in this ER core structure, we can separate the flux path into three paths. For each path, this will only go with this half of this total flux. In this case, the magnetic flux distribution will be distributed in a more even form, and the eddy current loss in the core can be significantly reduced. With this kind of ER core, and with the uniform B field distribution, the eddy current loss can be reduced. The benefit for this kind of winding loss is that the uniform B field will lead to a lower leakage inductance, and that will also lead to kind of smaller winding loss. However, the main reason for this high winding loss is that, as we can see here, it's a non-interleaved structure. If we consider the H field distribution in the primary side winding, we will see the MMF field will be accumulated from the first layer to the 8th layer. The highest MMF will reach to 8 times of the current. And if we talk about this normalized AC winding resistance per layer, we will see from the first layer to the 8th layer, the AC resistance will be increased. If we just have a look at the winding resistance per layer, we will say from the first layer, it's around just 0.68 times of this DC resistance. If we further increase this part to the AC terms, the AC resistance will come like around 10 times DC resistance, which means the total resistance for this kind of 16 turns will just equals to around 5 times of DCR, and the AC resistance of this structure will come to over 4 times of this DCR. And the AC winding resistance is significant with such a non-interleaved PCB winding. However, we always have these opportunities to just use a sandwich structure, although we cannot achieve the perfect interleaving. As we can see here, the shielding of this primary side winding provides a constraint for the E field, and all the E field will be constrained inside this primary side, so that we can easily achieve this sandwich structure with these two separate sides on top or bottom of this transformer, and there won't be some insulation issues. If we just use such a sandwich structure, as we can see in the page 12, the H field is shown here, and we can see the MMF will just decrease to the half, and the highest MMF will only come to 4 times of the current. If we see from this part for this kind of normalized AC winding resistance, we will just put this one into 2 parts due to the kind of the sandwich structure. We will see from the 4th layer to the 1st layer, and from the 5th layer to the 8th layer, the winding resistance still increase, but the highest winding resistance is only 4.3 times of the DC resistance. It's not so severe. Talk about the total resistance, it's only 3 times of the DC resistance, and the AC winding resistance will be only 2 times of this DC winding resistance. And the normalized AC resistance is reduced with 50% with such sandwich winding. In this case, we get some feeling that we may just to use the sandwich winding structure to easily reduce the winding loss. However, we will still see this part compared with the additional 3 turns. There are huge winding resistance with the 1st layer and the 8th layer, which means although we can still use the sandwich winding, and the MMF impact is still high in this kind of the 1st layer and 8th layer. So, or maybe what we can do is that we can further reduce the turns number and to have a lower winding resistance. However, the thing comes to, if we just reduce the turns number, the B field just inside the core will just increase, or we have to just lift the switching frequency to just allow us to use a less turns number. This one just bring us some just new idea to just further optimize our transformer design with the different design objectives and design parameters. Here comes the optimization process for the transformer with the sandwich winding. First, that we will just assume the switching frequency equal to 200 kilohertz, and we will just assume the turns number is equal to 12, as we will see just on the previous page. If we just use 16 layers, and the additional 2 turns will just have significant loss. So we will start with this turns number equals 12. And the first step is that we will step the transformer dimensions with this core radius and the winding width, R and C, for the footprint and the loss trade-off. And the second step is that we will repeat the step 1 for the sweeping of turns number. And then I will do the step 3 for the repeating step 1 and 2 with the sweeping of the switching frequency. Here is the optimized transformer dimensions with the core radius and the winding width. As we can see, we can just draw the contour based on the total loss versus these 2 design parameters. And also, we can also just calculate the footprint based on the core radius and the winding width. As we can see here, we will just find the optimal result with the given footprint to find lowest transformer loss. and then we can just draw a line to get the curve. In this case, we can just find an optimal loss and footprint trade-off with a given turns number and given frequency. And the transformer is optimized based on such a loss and size trade-off. And also we will just have a preferred smaller winding loss with a better thermal management. The next step is that also we can repeat the same exercise and to get optimized transformer turns number. From this one, we will just have these 16 turns as we can see here. And as we can see, the winding loss for the 16 turn case is significantly higher compared with this 12th turn optimization. And if we just have these 8 turns in optimization in the same page, we will see the winding loss will just further reduced, but the core loss will increase significantly with the same footprint. And in this case, we will find that 16 turn optimization has a significant winding loss compared with to smaller turns number design. And then we will just use this 112 centimeter square for the footprint as we optimized in this step 2. As for this kind of step 3, we will just compare the switching frequency impact under the footprint equals to 112 centimeter square. In this case, we can sweep the different frequency based on this case, and we will find that in the region between switching frequency equals to 150 kilohertz to 250 kilohertz, we will just see this kind of best optimal point for this transformer loss with a given footprint. In this case, we will just finally design our transformer at this 200 kilohertz. Another benefit for this part is that our insulation performance. As we can see, although for this kind of PCB winding, we can just have a better insulation with a thinner FR4 thickness. In the E-field simulation, there are still 4 hot spots just in the corner. That is because the right angle leads to a sharp end, and that will lead to a just high hot spot as in the transformer design. To solve this part, we can just slightly increase the length for the center 4 turns and to create an arc section winding. And in this case, this arc section is selected to reduce the E-field in this FR4. And we will see the peak E-field will just drop from 16 kilovolts per millimeter to like around 10 kilovolts per millimeter. And that one will also increase the insulation capability. Next part, I will just talk about the fabrication process and some experimental results. As we can see, compared with the Litz based transformer, how easy this fabrication can be. We can just easily get this winding with this kind of FR4 as the insulation from our vendor. And this one is just simply to add another 2 insulation layer, FR4 layers on the top and bottom of this transformer encapsulation. And also we can just coat this conductive shielding ourselves and also just to lead to this stress grading terminals here. And everything just, and for the toughest part, this one can be easily by the just PCB machines. And the other parts are just relatively easy compared with to control the air voids inside the epoxies. Here shows a hardware prototype demonstration. As we can see here, this part is the entire PCB will be just the height of this one will determine by this kind of PCB-based winding of transformer. And so the power density can be lifted compared with the Litz-based transformer almost 2 times. And this one just can come to this 7.4 kilowatts per liter power density. And if we just see this kind of test waveform, we will see that the ZVS can be achieved in all power level. And the peak efficiency can reach 98.8%. And the full load efficiency will just drop 0.1%. And also the power density will be 2 times higher with this Litz-based transformer and with a comparable efficiency. That is the benefit due to this PCB winding based transformer. And As we can see here for this kind of insulation test result, compared with this Litz-based transformer, the PCB-based transformer will just have almost 2 times higher partial discharge inception voltage. And also the partial discharge free will just have a just better performance with this insulation test result. Also, if we can see here with this comparison between the Litz and PCB windings, we will see although the width and length will be slightly increased from the dimension part, the profile is much smaller and the volume will be kind of smaller. With the almost same loss performance, our insulation level is lifted almost 2 times. Also, finally, we come to the summary. We proposed a 15 kilowatt PCB winding transformer design for this solid state transformer application with this medium voltage insulation. And the transformer structure will be optimized to reduce losses, especially in the AC winding loss, where the turn-to-turn resistance is a concern. The insulation structure will be modified with this arc section to prevent the high electric fields in the corner. And also these improvements have been tested on a 800 to 400 volts, 15 kilowatt CLLC converter, which achieved a peak efficiency of 98.8% and was free of partial discharge and up to 17 kilovolts. However, one question is that this one is designed based on 15 kilowatts. Is this one enough for a module with a solid state transformer? And how to further improve this kind of power levels? And what is the limitations for the PCB winding based on transformer design for these applications? And maybe you can come to the dialogue session and I will show you with some newer achievements with you at my bench 24. And thank you, and that's all for my presentation.